This video is another story of human innovation and accomplishment. The story of the early explorers and the incredible system they created to enable global exploration. You are probably familiar with latitude and longitude, the coordinate system used to define locations on the surface of the Earth. This system has ancient roots. It appears the early Greeks were the first to propose a global coordinate system. Their system evolved over thousands of years into the one we use today. Lines of latitude are drawn parallel to the equator, defining north-south coordinates. The equator is 0 degrees. Lines of longitude radiate from the poles, defining east-west coordinates. 0 degrees longitude passes through Greenwich, England. Intersecting lines of latitude and longitude define a location. For instance, the Great Pyramid at Giza is located at latitude 29.98 degrees north, longitude 31.13 degrees east. Determining your latitude and longitude today is pretty simple. Even most smartphones carry GPS technology, displaying your location with precision. Let's look at how the early explorers and surveyors were able to determine these coordinates with only a clock and a knowledge of the solar system and the night sky. Determining latitude is relatively simple. In the northern hemisphere, your latitude is the angle between the horizon and Polaris, the North Star. Polaris sits apparently motionless directly above the Earth's North Pole. There is an equivalent celestial method for the southern hemisphere. The first Portuguese explorers, with an eye on Polaris, crossed the Atlantic following lines of latitude. You can easily create a device to measure this angle. View our inclinometer video for instructions on measuring the angle to Polaris. Using an inclinometer at my location reveals an angle to Polaris of 45 degrees. My latitude is 45 degrees north. With latitude determined, we will now turn to determining longitude. This is not easy. Humankind has struggled with the longitude question for thousands of years. The problem is the rotating Earth. Unlike latitude, there is no apparent motionless star, no Polaris to define longitude with. All the stars appear to be in motion from the east-west perspective of longitude. By the 18th century, all seafaring nations were focused on the longitude problem. If the stars were to play a role in determining longitude, some method or device for determining the Earth's position at any time in its rotation was needed. In the late 1700s, just such a device appeared, with the unveiling of the world's first precision marine chronometer. John Harrison, an English clockmaker, had accomplished what many of the most celebrated minds of the era couldn't. He had solved the longitude problem. I won't dwell on the story of Harrison and his clock, but it is a dramatic and inspiring story. If you get a chance, read Davis Sobel's book Longitude. An amazing story. His clock was the first timekeeper to reliably and precisely keep time on a pitching rolling ship. His chronometer revolutionized navigation. One way to think of a clock like Harrison's is that it is a mechanical model of the rotating Earth, accurately following the 24-hour period of a day. With this device, it now became possible to determine longitude from any location on the planet. Here's how this works. We'll use a clock and the sun. The first line of longitude, 0 degrees, and also called the prime meridian, passes through Greenwich, England. This is an arbitrary location, agreed upon by a majority of nations. This line of longitude extends from the north to the south pole, passing through Greenwich. When solar noon arrives at Greenwich, England, the sun is at its highest altitude, and at this moment it sits directly above the prime meridian, 0 degrees longitude. This is solar noon, or sun transit time. Some of you will know that solar time and clock time are sometimes not the same. We will discuss that anomaly later. For this demonstration, we will assume that solar noon and clock noon at Greenwich are the same. Clock time and solar time at Greenwich agree. They both display 12 noon. As the Earth rotates, the Sun no longer sits above the prime meridian. It is now sweeping past other lines of longitude. The Earth rotates 360 degrees in 24 hours. That's 15 degrees per hour. 1 hour after noon in Greenwich, the noontime Sun now sits directly above 15 degrees of longitude. 2 hours later, it sits above 30 degrees of longitude. Five hours later, solar noon is approaching my neighborhood. Here in eastern North America, we are in a time zone, Eastern Standard Time, that puts us 5 hours behind Greenwich time. 12 noon here translates to 5 p.m. at Greenwich. You may see where we are going with this. If I can determine the time of solar noon, the moment when the sun is highest in the sky at my location, I will know how many degrees west of Greenwich I am located, my longitude. I can use a watch to determine time, and here is how we will determine solar noon. At solar noon, the sun sits at its highest above the horizon for that day. This means it casts the shortest shadow at that time. We are going to determine clock time for solar noon by monitoring the length of a shadow cast by the sun. This is the equipment I used. The short post casts a shadow onto a sheet of card. The card needs to be secured and level. To collect data, note and record the time. Then mark the end of the shadow. I started at 10 a.m., plenty early. The first few recordings were 20 to 30 minutes apart. As we got closer to noon clock time, I increased data collection to every 5 minutes. This is the important data. I finished data collecting at 2 p.m., but concentrating on 20 minutes before and after clock noon would have sufficed. Next step is to determine the time for the shortest shadow. I drilled a hole in the zero mark of this metal ruler and slid it over the post. The length from post to end of shadow is easy to determine. My best estimate here shows the shortest shadow occurred at 12:10, 2 5-minute marks past 12. Now to calculate our longitude. We have to relate our local time for the solar noon calculation to the time in Greenwich. We know that our time here, Eastern Standard Time, is 5 hours behind Greenwich time. So solar noon here occurred at 5:10 p.m. Greenwich time. This means the Earth rotated for 5 hours and 10 minutes from zero longitude in Greenwich. At 15 degrees per hour, 5 hours and 10 minutes translates to 77.5 degrees of longitude. According to my GPS, my longitude is actually 76.93 degrees west. My calculation missed by half a degree. That's an error of approximately 80 kilometers on the surface of the Earth. Here is the source of some of this error. It turns out that solar time varies from clock time throughout the year. If you're interested in why this happens, view our video, The Equation of Time. On the day I collected this solar data, that's December 30th, solar time was 2 minutes and 15 seconds behind clock time. This means that solar noon at Greenwich actually occurred at 12:02:15 p.m., not 12. This means the Earth actually rotated for 5 hours, 7 minutes, and 45 seconds from Greenwich. Doing the math at 15 degrees per hour, this time we get 76.94 degrees. Very close, within 0.01 degrees of our actual longitude. An error of less than 1 kilometer. Not bad for watching shadows and recording time. The early navigators and surveyors not only used the sun, they were knowledgeable astronomers. Working at night, they used overhead stars and the best timekeepers of the period to determine longitude. Again, the time of transiting stars was compared to the time at Greenwich to calculate longitude. The maps produced by the early surveyors using these methods are remarkable. Visit hylaroad.com/longitude for more information about the people and math behind this story. And for a complete list of our science and technology videos, visit hylaroad.com. Follow the videos link.